All right, here's the second half of the projectiles worksheet. Number 5. A stone is thrown horizontally from a cliff 30 meters high with an initial speed of 20 meters per second. How far from the cliff does the stone strike the ground? What is the vertical speed of the stone as it hits the ground? We've got this cliff. We have the stone here being thrown horizontally. We do this. We want to find how far from the cliff. That's that thing. And then what is its vertical speed? So we want the final velocity in the y direction. Those are my two unknowns. We know the cliff is 30 meters high. Okay, it's headed down. If we count this as my starting spot, its initial speed, so that's all in the x direction, is 20 meters per second. If we're in meters, then we know my acceleration is g, which is down 9.8 meters per second squared. Okay, again, we want delta x equals vx times t. We do not know the t, so we have to go look in the y direction. So we're looking in the y direction, and we want to find the time. We know the change in position. We know the initial velocity in the y is equal to 0. And we know the acceleration. So if we use the change in position equals v(i)y t plus 1/2 at squared. This goes to 0, because the delta y is 1/2 at squared. Therefore, 2 times delta y divided by a, take the square root, and we get time. The square root of 2 times negative 30. That's my delta y. The acceleration is negative 9.8. Move the units off, make it a little less cluttered. Whoops, get it up on the screen so you can see what we're doing. And then we're going to take the square root of 2 times negative 30 divided by negative 9.8. And we get 2.47 seconds for all that distance. And now we can go back and solve for part A that we were looking at. Delta x equals vx, which was the 20 meters per second, times the time of 2.47 seconds that we just solved for. And we get delta x is 49.4 meters. Okay, and then in part B, it says what is the vertical speed of the stone as it hits the ground. So we don't want vx, we're looking in the y. We want final velocity in the y direction. If we look at our equations, no final velocity there. There's a final velocity, initial velocity, acceleration, and time. We could use that one. Here's the final velocity, initial velocity, acceleration, and change of position. So we'd use either one of those two equations. Doesn't matter. Since we now have the time, we can just solve this. So initial velocity 0 ends up being about the same. We can do them both ways if you want. So Vf equals v(i)y plus at. That's 0. So final velocity in the y is acceleration 9.8 meters per second squared times the 2.47 seconds. And we'll end up with something in meters per second. Negative 9.8 times 2.47, and we get negative 24.2. And it says it's going down, which makes sense because we are going down. We're falling through the air. Let's try it the other way just to see if it works. Vf squared equals v(i)y squared plus 2a delta y. Again, that's 0. So Vfy is just the square root of 2 times acceleration times change in position. Okay, and so this is just the square root of 2 times negative 9.8 times negative 30. And we'll get something in meters per second. So the square root of 2 times negative 9.8 times negative 30. And we end up with 24.2. Okay. Now this one, it didn't show up negative. It came out of the square root. So on this one, if you do it this way, you have to realize it's going down, and you have to go add that negative back on. So there, the math kind of doesn't work for us, just because it doesn't automatically put that negative on for us, but we know it's going down, so we have to add it there. All right, so that was number 5. Let's take a peek at number 6. We have a golfer now hitting a golf ball. It gives it an initial velocity of 40 meters per second at an angle of 30 degrees above the horizontal. So now we're launching 30 degrees above the horizontal. It is at initial velocity of 40 meters per second. How long does the ball stay up in the air? Okay, so when it does all this thing, it'll land down here somewhere. We know we're going to have the velocity in the x, initial velocity in the y, and we're looking for time. How long is it flying through the air? The total time. A couple different ways we can find that. If we know it's going to land at the same height, which everything we're doing in here will basically land at the same height. Sorry, see this question. If we do that, then we know my change in position in the y is 0 for the total trip, okay? Because it lands at the same height it took off at. Okay. We also know the acceleration is g, which is negative, and we're doing meters per second, so 9.8. And so if we know delta y, and we know a, we can find the initial velocity in the y, and we're looking for time, we can use this one. Okay? Now, the tough part about this one is it's a quadratic, right? So that's not a whole lot of fun. If the initial velocity in the y was 0, that'd be pretty good. Okay? This one, we also have all that stuff, but it doesn't have time. So we really would like to look at this guy. And so that makes it a little more difficult in that we have final velocity in the y equals initial velocity in the y plus at. There's my t, but I don't have the final velocity in the y, unless I go halfway. So you have your choice. You can either solve a quadratic, or we can do this and just solve this simple one and then just double our time. I'm going to go with the simple one and double our time. So we're going to go with this. We know the final velocity in the y at the top is 0. Okay, so that makes that 0. So we need this initial velocity in the y. So VIY, because it's the opposite side, it's the sine, so it's hypotenuse times the sine of the angle, which is the 40 times the sine of 30. Sine of 30 is half, so that's just 20 meters per second. Okay, so now we can punch that stuff into, solve this for t. T is negative VIY divided by A. So that's negative 20 meters per second over 40, no, I'm sorry, it's A, not the initial velocity, negative 9.8 meters per second squared. Okay, so 20 divided by 9.8 is going to be a little over 2. 20 divided by 9.8, they were both negatives, so it all ends up canceling off. You can type the negatives in if you want, but you'll still get a positive number, 2.04. Remember, that was the time to the top. So we're going to double that to get the total time. So 4.08 or 4.1. So time total is 4.1 seconds. Okay, so that was part A. Part B, what is the maximum height of the golf ball? So now we're looking for what is its height right here. So we're looking for the change in position. Okay, so what is delta y? Well, now we have more info. We have time to the top. The time to the top was the 2.04 seconds. We just solved for that on the last one. So now we have time to the top, because that's what we're going to. We have the final velocity at the top. So we could use this. We know the initial velocity. We know the time to the top. So that one would work fine. We know the final velocity at the top and the initial velocity, so that one would work fine as well. Either one you want to go with, and you have two choices. This one's already solved for delta y, so let's just try him. Okay, so VIYT plus 1/2 AT squared. And we can just plug our in. Initial velocity in the y was 20 meters per second times the time of 2.04 seconds, right? Because we're just going to the top. And this is plus 1/2 times negative 9.8 and 2.04 squared. So 20 times 2.04, and we're going to add that to 0.5 times negative 9.8 times 2.04 squared, and we get that we went 20.4 meters high. Okay, so there's our time height that we went. And then what is the range of the golf ball? So delta x equals vx times t. We could go use the range equation. Let's try a different color here. We could use the range equation. Remember that was x equals vi squared sine 2 theta over negative g. Okay, which would work. Or we could use this because we've already solved for the total time. So this looks super easy. Although we have to solve for Vx. So whichever way you want to do it, doesn't matter. Vx is just the hypotenuse times the cosine of theta, side adjacent. So that's 40 cosine of 30, which is going to be about 33 or something. 40 cosine of 30, 34.6. That was pretty easy. So once we have that, it's just going to be 34.6. And we're going to multiply that times my, now we want total time because we're going the total distance. So 4.1. And we get 142 meters. We should get the same thing if we do that. Let's try that. Let's try this again. So delta x equals the 40 meters per second squared times the sine of 2 times theta. All that divided by negative 9.8. And we get 40 squared sine of 60. And all that divided by 9.8. And we get 141.4. It's basically the same. We've rounded a lot here and there. So 141.4 and 142, basically the same thing, right? Remember, we rounded off this, we rounded off that. So it's a rounding error. All right, so there's number 6. All right, let's look at my last two really quick here, 7 and 8. We might zip through them pretty quick. They're probably very similar to what we've already done. Number 7, if an object leaves the ground at a 66-degree angle with an initial speed of 50, what its initial vertical velocity? Okay, we just did that. So we're just looking at initial vertical. It's just going to be the hypotenuse times the sine, because it's the side opposite. So 50 times the sine of 66. How long till it reaches its maximum height? Okay, we did that thing. Same thing we just did. And how long until it reaches the ground again? Well, that's exactly B. It takes time up as it does go down. How about Gary? Gary, the quintessential soccer player, kicks the ball at an angle 43 to the horizontal and velocity of 15 feet per second. Find the initial horizontal and vertical. Okay, that's just horizontal is the cosine and vertical is the sine. Time it takes, again, we're doing the same thing we just did. Total time, again, we just double it. Total distance, Vx, we already have Vx, we just solve for the total time, so just multiply there. And then the total vertical distance to the peak height, again, we're just looking for delta y. So both of these two are what we just did, basically, in number 6. So 6, 7, and 8 are all very similar. So look at what I did for 6, plus I've given you the answers on Schoology, so you can go look there as well.